Welcome to this comprehensive guide on leveraging hash set and queue data structures within your Unity 3D gameplay systems. These powerful tools can significantly optimize your game's performance and logic, offering efficient ways to manage collections of data. We will delve into the core functionalities and practical applications of both, providing a solid foundation for beginner game developers. Throughout this tutorial, we'll explore the fundamental concepts of both hash set and queue, demonstrating their practical applications through step-by-step examples in Visual Studio and Unity. You'll see how to implement them in C# and integrate them directly into a Unity project, making the learning process highly interactive and practical. First, let's understand hash set. It's a collection that stores unique elements, meaning no duplicate values are allowed. This makes it incredibly efficient for checking if an item already exists within the collection, as well as for adding new items without worrying about redundancy. This uniqueness constraint is a key feature that differentiates it from other collection types. Unlike lists, hash sets do not maintain any specific order of elements. Their primary strength lies in very fast lookups, insertions, and deletions, often performing in near constant time, denoted as O. This means that no matter how many items are in the hash set, the time it takes to perform these operations remains almost the same, which is a huge advantage for performance-critical applications. In game development, hash sets are ideal for managing unique entities like active quests, discovered items, or enemies within a specific area, preventing redundant entries. For example, if you have a system that tracks discovered locations, a hash set ensures that each location is recorded only once, even if the player visits it multiple times. Consider a scenario where you need to track all enemies currently within a player's attack range. A hash set ensures each enemy is counted only once, even if multiple detection events occur. This prevents issues like an enemy being targeted twice or receiving duplicate damage calculations, leading to more reliable gameplay mechanics. Let's dive into Visual Studio to see how to declare and use a hash set. We'll create a simple script to manage a collection of unique enemy IDs. This will demonstrate the basic syntax and structure required to incorporate hash sets into your C# projects, laying the groundwork for more complex implementations. Adding elements is straightforward with the add method. If an element already exists, add simply returns false without adding a duplicate, which is very useful for conditional logic. This behavior allows you to easily check if an item was newly added or if it was already present in the set, streamlining your code. To check for an element's presence, use contains. This method is incredibly fast, making it perfect for frequent checks in gameplay loops, such as determining if a player has a specific item or if an enemy is within a certain zone. Its performance ensures these checks don't become a bottleneck. Removing elements is done with remove. This also returns a Boolean indicating if the item was successfully found and removed. This return value can be used to confirm the removal or to handle cases where the item was not present in the hash set to begin with, providing robust error handling. Now, let's integrate this into Unity. Imagine a trigger zone that detects enemies. When an enemy enters, we add its ID to our hash set. This practical example will show how hash sets can be used to dynamically manage game object states based on their interactions within the game world. In our Unity script, we'll use onTriggerEnter to add enemy IDs and onTriggerExit to remove them, ensuring our hash set accurately reflects active enemies. This real-time updating of the hash set based on physics events is a powerful way to maintain an up-to-date collection of relevant game entities. This setup provides a highly efficient way to manage dynamic groups of unique game objects, crucial for systems like aggro management or area of effect abilities. By using a hash set, you can quickly determine which enemies are affected by a spell or which targets an AI character should prioritize, leading to responsive and accurate gameplay. Next, we turn our attention to the queue data structure. A queue operates on a first in, first out, or FIFO principle. This means that the first element added to the queue will always be the first one to be removed, ensuring a strict order of processing. Think of it like a line at a store. The first person in line is the first person served. This sequential processing is its defining characteristic, making it ideal for scenarios where the order of operations is critical and must be strictly maintained. Queues are perfect for managing tasks that need to be processed in a specific order, such as command buffers, action sequences, or network message handling. They ensure that no task is skipped or processed out of turn, which is vital for maintaining game state integrity and preventing unexpected behavior. For instance, in a strategy game, player commands like move unit, attack, or build can be queued up and executed sequentially. This allows players to issue multiple commands without them being executed simultaneously or in an incorrect order, providing a smooth and predictable control experience. Let's switch back to Visual Studio to implement a queue. We'll create a queue of player commands. This will illustrate how to declare and initialize a queue in C#, preparing it to store a sequence of actions or messages. To add an item to the end of the queue, we use the enqueue method. This is how commands are added to our processing list, always appending to the back of the line. Each new command waits its turn, ensuring that the FIFO principle is upheld. To retrieve and remove the item at the front of the queue, we use the queue. This executes the next command in line, effectively processing the oldest command that was added. This operation both returns the item and removes it from the queue, advancing the line. If you only want to look at the next item without removing it, the peek method is available. This is useful for previewing upcoming actions or checking the next command without altering the queue state, allowing for conditional logic based on what's next in line. Now, let's see this in action within Unity. We can simulate player input adding commands to a queue, which are then processed over time. This will provide a visual and interactive demonstration of how a queue manages and executes a series of player-initiated actions. Our Unity script will have a method to enqueue commands based on player input and another method, perhaps called an update, to dequeue and execute them. This separation of concerns allows for clear management of command input and their subsequent processing, making the code modular and easy to understand. This ensures that complex player actions or AI behaviors are handled in a predictable and orderly fashion, preventing race conditions or out-of-order execution. By strictly adhering to the FIFO principle, queues provide a reliable mechanism for managing sequences of events in your game. A helpful tip for hash sets: when storing custom objects, ensure you override equals and get hash code methods. This is crucial for correct uniqueness checks, as the hash set relies on these methods to determine if two objects are considered identical. Without them, it might not function as expected. Without proper overrides, the hash set might treat two objects with identical data as distinct, leading to unexpected behavior and potential bugs. For instance, if you have two enemy objects with the same ID but different memory addresses, the hash set would consider them unique unless equals and get hash code are correctly implemented. For queues, always check if the queue is empty using count equals 0 or any from linq before attempting to dequeue or peek to avoid errors. Trying to dequeue from an empty queue will result in an invalid operation exception, which can crash your game. Defensive programming here is key. Another optimization tip: for very large collections, consider pooling objects rather than constantly creating and destroying them, especially when using queues for object recycling. Object pooling is a design pattern that significantly improves performance by reusing objects instead of allocating new memory for them repeatedly. This technique, often called object pooling, significantly reduces garbage collection overhead, leading to smoother gameplay and better performance. By returning objects to a pool when they are no longer needed and retrieving them from the pool when required, you minimize the performance impact of memory allocation and deallocation. Both hashset and queue are part of the system. Collections, generic namespace, so remember to include using system. Collections, generic, at the top of your C# scripts. This directive makes these powerful data structures available for use in your code, allowing you to leverage their benefits. Understanding when to choose between different data structures is key. Hash sets excel at uniqueness and fast lookups, making them ideal for managing distinct items. In contrast, queues ensure ordered processing, perfect for sequential tasks where the order of operations is paramount. By incorporating these data structures effectively, you can build more robust, efficient, and scalable gameplay systems in Unity 3D. Their proper application can lead to cleaner code, fewer bugs, and a more optimized game experience for your players. Experiment with these concepts in your own projects. The best way to learn is by doing and seeing the performance benefits firsthand. Try implementing a simple quest log with a hash set or a command buffer with a queue to solidify your understanding and explore their potential. Thank you for joining this guide on hash set and queue in Unity 3D. We hope this has provided a solid foundation for your game development journey, equipping you with valuable tools to create more dynamic and efficient gameplay systems. Keep exploring and building.